Let's get started on part 2 of chapter 10. In part 1, we did a review of TCP/IP. We discussed the subnet mask, the IP address, the default gateway, the IP config, and the ping command. Now let's move on to understanding IP for addressing. A packet is made up of data and header. And a header shows where the packet is going to. And a packet header contains the IP address of the destination computer. An IP address is made up of 32 bits. And as you know, a bit is represented as a 0 or a 1. Let's look at binary. Let's do a review of binary math. Now, when one computer communicates with another computer, the only thing one computer can send to another computer is positive and negative impulses, which are represented as zeros and ones. So, if this computer can only send positive and negative impulses to the other computer, how can it possibly send the number 7? And the answer is different combinations of positive and negative impulses represent different values. So how is it that 5 negative impulses and 3 positive impulses represents the number 7? So this is binary math. So we have 8 positive and negative impulses. We have 8 positive and negative impulses, and each bit represents the absence or presence of a value. The first value is 1, the second is 2, the next is 4, 8, 16, 32, 64, 128. So if we have 7 zeros and a 1, then that represents the number 1. If we have 6 zeros, a 1 and a 0, that represents the number 2 because it indicates we just have a single 2. If we have 6 zeros and 2 ones, that represents the numbers 3 because we have a 1 and a 2. If we have 5 zeros and 3 ones, then that represents the number 7 because we have a 1 and a 2 and a 4. How about this example? If we have a 1 followed by 7 zeros, that represents the value of 128. If we have a 1, 6 zeros, and a 1, that represents the value of 129. And if all 8 bits are set to 1, that represents the value of 255 because it's 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. When all 8 bits are set to 1, the highest number is 255. Let's look at what we call low order and high order bit patterns. If the 2 lowest order bits are set to 1, then that's 3. If the value 3, if the 3 lowest order bits are set to 1, then that represents the value 7, because you have a 1, a 2, and a 4. And if you can understand that 3 ones are equal to 7, then you have a career in the computer field. 4 zeros and 4 ones represents the value of 15 because you're at 1 plus 2 plus 4 plus 8. Now let's look at higher order bits. If the higher order bits are set to 1, that means you have 128 plus 64, which is 192. If the 3 higher order bits are set to 1, then that's equal to 224. Wait a minute, I thought we said 3 bits are equal to 7. If they are lower order bits, they're set to 7. But it's equal to 7. But 3 higher order bits are equal to 224. And if the 4 high order bits are all set to 1, that's 128 plus 64 plus 32 plus 16, which is equal to 240, which we will see again in the subnet mask. So the TCP/IP header has a 32-bit address space. If one computer is going to send a packet to the other computer, the computer might be sending the number 7 to the other computer. That's the data which is being sent. But the packet header indicates the IP address of the destination computer. You and I might see that as 129.15.2.1, but really that packet header is going to have a series of positive and negative impulses that'll represent this value of 129.15.2.1. The first octet, 1, 6 zeros and a 1, represents 129. The second octet, 4 zeros and 4 ones, represents 15. The third octet, 6 zeros, a 1 and a 0, represents 2. And of course you can see the last octet represents the value 1. TCP/IP has a 32-bit address space. So can an octet be 999? No, it can't, because there are only 4 bits in an octet, and when all 4 bits are set to 1, you get 255. There are 8 bits in an octet, and if they're all set to 1, the highest value you can have is 255. 8 bits, 4 octets, a total of 32 bits in an IP address space. 32 bits in an IP address. Let's look at an IP address and subnet mask in decimal and in binary. Now you and I would go to a workstation, and to assign it an IP address we would type in 131.15.0.129, assuming that was the IP address we wanted to assign, and we would type in a subnet mask of 255.255.0.0 to indicate that the first 2 octets are network ID. But that's not how the computer sees it. The computer sees everything in binary. This is how the computer sees it. This would be the IP address, and the lower line would be the subnet mask. So 131, you can see that this octet is 128, plus 2 is 130, plus 1 is 131. The next octet, 4 zeros and 4 ones, is 15. The next octet, 8 zeros is 0. The next octet, a 1 followed by 6 zeros and a 1, is equal to 129. Now let's look at the subnet mask. You and I might write 255.255.0.0, but the computer sees it as a string of 8 ones followed by a string of 8 ones followed by a string of 8 zeros followed by a string of 8 zeros. This is what we would call a 16-bit subnet mask. Now let's look at the 3 IP address classes. A Class A subnet has a subnet mask, a Class A network has a subnet mask of 255.0.0.0. That's a subnet mask of 8 ones. 255 is 8 ones in binary. That's an 8-bit subnet mask, and you could simply represent that by typing /8. There are 16 million potential host IDs in a Class A network because you have 24 bits with which to assign host ID, and 2 to the 24th is 16 million. Conversely, at the other end of the extreme is a Class C network, and the default subnet mask for a Class C network is 255.255.255.0. The computer sees that as a string of 24 ones. So a Class C subnet mask is a 24-bit subnet mask. Now let's look at assigning IP addresses, and this is a real tricky section. Given a network ID of 1.0.0.0 with a subnet mask of 255.0.0.0, what would the IP address be of the first host, of the 254th, 255th, 256th? Well, I think the first one is easy. It's network 1.0.0.0, so the first host would be 1.0.0.1. That's obvious. And the next one would be 1.0.0.2, .3, .4, .5. The 254th host would have an IP address of 1.0.0.254. And the 255th host would have an IP address of 1.0.0.255. Wait a minute, I thought the host ID can't be 255. Well, that's true that the last octet can't be 255 in a Class C network, but the rule is you can't have 255 in the entire host ID. Notice we have 3 octets for host ID, and not all 3 octets are 255. So this is totally okay the 255th host would be 1.0.0.255. Okay, here's where it gets tricky. Would you assign the 256th computer, would you give it an IP address of 1.0.0.256? It makes sense, but you couldn't, because there are only 8 bits in an octet. And when all 8 bits are set to 1, it's 255. So how do you represent the next value higher than 255? To find the next value higher than 1.0.0.255, this octet becomes 0, and the next octet becomes 1. So this would be the correct IP address for the 256th host, 1.0.1.0. And this is a very tricky thing to understand. This is exactly what you would type in as an IP address on the 256th computer, and it really confuses many people. The 255th is not so confusing, but the 256 would be 1.0.1.0, and the 257th would be just one more, 1.0.1.1. And even trickier, the 513th host would be 1.0.2.1. Very difficult concept to understand. Now let's talk about subnetting. Subnetting is where we add an additional network because we've built a new building, or we have added another floor to our building. We add a new network, and then we have to assign IP addresses and network IDs to the computers in that network and not violate the rules of IP addressing. So we get 2 subnetting examples, example 1 and example 2. Let's start with example 1. What we're going to do is add an additional network or networks, and we have to find out what the new subnet mask will be. What's the new subnet mask going to be? So if we start out with our original situation, you and I, as network engineers, have been assigned the IP address of 131.15.0.0 to be used in the building that you and I are responsible for. So the first workstation would be 131.15.0.2, and the next one would be .3, and the next one would be .4, and of course the router would be 131.15.0.1. Fine, that's just a review. But then when we add an additional network, because due to growth in the company, we install the computers and we connect the 2 networks together with a router, and the question is, what is the IP address going to be on these computers on the second network to the right? Well, it seems to me if this last workstation is 131.15.0.4, couldn't we just make this one 131.15.0.5? No. We couldn't do that because that would violate the rules of IP addressing. We would have 2 different networks that were both called 131.15, so we can't do that. Okay, let's try using 131.15. No, can't do that. Another building has been assigned 131.15. Okay, let's use 131.14. Can't do that. That's been assigned another building as well. We've been assigned a single network ID, 131.15, and we got to find some way to assign different network IDs to the different networks that we have. The statement of the problem is that we need a network ID for the second and any additional segments that we're going to add. And the solution is to use the 3rd octet for subnet ID. The solution is to move the subnet mask 1 octet to the right and then use the 3rd octet as subnet identifier. So here's how we do it. In the original situation, we have 131.15.0.1 with a subnet mask of 255.255.0.0, or you could just say it's a 16-bit subnet mask. If we push the octet over, if we push the subnet mask over 1 octet to the right, 8 bits to the right, you can now see that the new subnet mask is 255.255.255 because we are using this third octet as subnet identifier. Notice the new subnet mask is a 24-bit subnet mask. And then we use the third octet for the subnet identifier. So here's what it would look like in production. To the left, we have our original network, which is 131.15, and the workstations are .2, .3, .4. But notice we have used the third octet to identify this network as subnet 1. What we have done on every computer here is we've pushed the subnet mask over one octet to indicate that that third octet is used for subnet identifier. Now we come over here and we do the same thing. Each computer is going to be 131.15, so that's consistent with the IP address that we've been assigned, and each workstation is going to be .2, .3, .4, but notice the third octet differentiates this network from this network. This network here indicates that it's subnet 1. The third octet tells us that. This network indicates that this is subnet 2. So now let me show two more segments. Let me just pull this router down, and now we can see that 4 different segments are coming off the router. Now they all start out with 131.15, and then the workstations are .2, .3, .4. But what's different on these segments is that the third octet is used to differentiate between subnets. So in subnetting, we move the subnet mask 1 octet. We move it 8 bits to the right, and we use the third octet as subnet identifier. Now let's look at example 2. In this example, we're only going to push the subnet mask over 4 bits instead of 8 bits to the right. In this situation, what does subnetting do to the number of network IDs? Well, it increases the number of network IDs. That's why we do it. But what does subnetting do to the number of host IDs? It decreases the number of host IDs. In other words, moving the subnet mask to the right reduces the number of bits in the host ID and reduces the potential number of host IDs. So how far to the right should you move the subnet mask? And the answer is far enough to give you additional subnet IDs, but not so far that it reduces the number of host IDs by much. So this is our original configuration, 131.15 with a subnet mask of 255.255.0.0. That's a 16-bit subnet mask, and there's 16 bits in the host ID. Now, in the previous example, we moved it over a full 8 bits. Changed the new subnet mask to 255.255.255 so we could use the third octet for subnet ID. But notice what it does to the number of host IDs. The host IDs is now reduced to only 8 bits in the host ID, and that kind of cuts deeply in the host ID. So here's what we do. Instead of moving the subnet mask over 8 bits, we move it over only 4 bits. Now you can see I pushed the subnet mask over only 4 bits, and that leaves 16 bits in the host ID. Subnet mask is now a 20-bit subnet mask, and these 20 bits are represented as 255.255.240. This is the new subnet mask. So when we calculate a new subnet mask, we 1. Determine how many subnets are required. 2. Determine how many bits are required to represent the number of subnets. 3. Convert the bits to higher order bits and convert to decimal to calculate the new subnet mask. So how many subnets do we need? Do we need just 2 or 3 additional subnets, or is this company really growing and we might need 10 or 20 subnets? In this example, we will say that we need an additional, we need a total of 15 subnets. That's the given. And then if we need to divide it into 15 subnets, what's the new subnet mask going to be? So number 2, we determine how many bits are required to represent the number of subnets. How many bits are required to represent the number 15? And the answer is 4 bits. We convert those bits to higher order bits and convert the higher order bits to decimal, and that is our new subnet mask. The 240 indicates that we have pushed the subnet mask over not an entire octet to the right, but only 4 bits to the right. So to increase the number of network IDs, we move the subnet mask to the right. The farther to the right you move it, the greater the number of network IDs that you have it, but the lesser the number of host IDs that you are left with. And this concludes part 2.